Hello and welcome to another spaceflight video. In this video, we will be talking about RocketLab. While RocketLab is mainly thought of as a launch provider, they have been branching out with the end goal of becoming a more economically diverse space systems company. To help them achieve this goal, they recently acquired SINCLAIR Interplanetary, a company devoted to producing the cheapest and most reliable hardware for small satellites. In addition to using this company to strengthen the unstable satellite hardware supply chain, hardware produced by SINCLAIR Interplanetary is also going to be incorporated into their Photon Satellite Bus. So now you're probably wondering, what the hell is Photon? Photon is off-the-shelf satellite hardware that contains the satellite's control systems, flight computers, batteries, fuel tanks, and engines. It was created because Peter Beck, the CEO of RocketLab, realized that satellites took a minimum of 18 months to be developed. This meant that the development time of the satellites was a major barrier to entry. So if you produced a product that reduced development time, then more people would be able to build satellites, and RocketLab's Electron rocket would get more customers. Also, the final stages of rockets are effectively small satellites. They have guidance systems, communications equipment, and engines. What's the point of launching two very similar satellites to do the same thing? Isn't that just a waste of hardware? Wouldn't it make more sense to just connect those two systems so that they share hardware? That is the purpose of Photon. During launch, the Photon flight computers will guide and control the Electron rocket. Then, after Photon is emitted from an Electron rocket, Photon switches into satellite mode where it begins to control the satellite. This is a good place to mention that Photon also simplifies the manufacturing process of satellites, because the satellite manufacturer only needs to produce the equipment that actually makes them money, which is usually easier to produce than the actual hardware used in day-to-day satellite management. Everything else is already included within the Photon. It's kind of like making brownies from a brownie mix instead of making them from scratch. In terms of its capability, Photon is capable of delivering 200 kilograms of payload to low Earth orbit that's approximately the same size as 2 adult males. The interplanetary variant is capable of bringing 40 kilograms, or 53 dozen large eggs, to interplanetary space, 20 kilograms, which is the mass of a mini fridge, on a Venus flyby, or 30 kilograms, approximately 640 Oreo cookies, into low lunar orbit. The low Earth orbit, or LEO, variant of Photon is powered by a Curie engine, named after Marie Curie, which runs on an unknown green monopropellant. Monopropellants are fuels that can produce thrust without needing a separate oxidizer. This usually means that they produce thrust by being decomposed over a catalyst of some kind. Green monopropellants are monopropellants that are less toxic than more mainstream monopropellants. The Curie engine produces 120 newtons of thrust in a vacuum, and yet again has an unknown specific impulse. Specific impulse is a measurement of the efficiency of an engine, kind of like the miles per gallon measurements in cars. Specific impulse is calculated by finding the velocity of the gas exiting the engine and dividing that by the acceleration due to gravity at sea level. Specific impulse is measured in seconds because when you divide the meters per second from the exhaust velocity by the meters per second from gravity, you end up with one leftover second. While this might all seem very complicated, you could probably just think of specific impulse as thrust divided by propellant consumption. One of the best ways to estimate the specific impulse of the Curie engine is by looking at the specific impulse of a hydrazine monopropellant engine. Hydrazine monopropellant engines tend to max out at around 230 seconds of specific impulse in a vacuum. The Curie engine should be just below that because it uses a slightly less efficient green monopropellant. The bipropellant hypercurie engine that powers the interplanetary Photon should have much more thrust and be much more efficient than its sibling engine, but we know very little about it. Also, it's important to point out that most rocket engines are bipropellant engines because bipropellant engines are much more efficient than monopropellant engines and are much less complicated than tripropellant engines. The Rutherford engine that powers the second stage of the Electron has a specific impulse of 333 seconds in a vacuum. That's almost 1.5 times more efficient than hydrazine monopropellant engines, and it produces much more thrust. And finally, we have the most important part of Photon, its naming scheme. As I said earlier, RocketLab also produces a rocket named Electron, and Photon is emitted from the Electron rocket. Just like how in physics, photons are emitted from electrons, which produces light. Important note, while I was editing this video, some news came out, and Photon was actually tested on RocketLab's 14th Electron launch, and apparently it performed perfectly. it didn't have any flaws, which is really cool. That's good news. Speaking of the Electron rocket, the Electron rocket is actually my personal favorite rocket. Yes, I like it more than the Falcon 9 and the Falcon Heavy. But now you're probably wondering, why do I like it more? Well, in my opinion, the Electron is actually more advanced than any current SpaceX rocket. The number one reason why Electron is so cool are its materials. The fuselage, fuel tanks, interstage, and aerodynamic fairing are all mainly composed of advanced carbon composites. Carbon composites are superior to the more standard aluminum alloys that SpaceX uses due to the fact that their specific strength is more than 3 times higher than that of aluminum's. Specific strength is equal to strength divided by weight, and is a measure of how much material you need to contain a certain amount of force. Electron needs to use much less material due to the higher strength-to-weight ratio of carbon composites. This means that the Electron is a much more mass-efficient rocket than the Falcon 9. A second advantage that the Electron has over the Falcon 9 are its engines. The Rutherford engine that powers the first and second stages of the Electron are entirely 3D printed, and are the first entirely 3D printed engines. This means that each engine can be produced in 24 hours without any human supervision. On top of that, the Rutherford engine is also powered using electric pumps. Most rockets are pumped using a turbine, which is spun using what is effectively a very small rocket engine. This means that some of the propellant in a traditional engine is not being used to produce thrust, and therefore is wasted. Because the Rutherford engine doesn't waste any propellant, it is actually more efficient than most other RP-1 and LOX engines. RP-1 stands for Rocket Propellant 1, and is effectively just highly refined diesel. It is also the fuel that powers most rocket engines, and LOX stands for liquid oxygen, and is used as the oxidizer in most rocket engines. The Rutherford engine has 303 seconds of specific impulse at sea level, which is better than SpaceX's Merlin 1D, which only has 282 seconds of specific impulse at sea level. The final thing that makes Electron so special is its payload to low Earth orbit. It can launch 225 kilograms to low Earth orbit, which allows them to launch 62% of all satellites. If they doubled the size of their rocket, they would only be able to launch 64% of all satellites. This means that the Electron is the perfect size for a rocket. Now, of course, you might be thinking, but making a bigger rocket has no downsides. You're wrong. Larger rockets are usually less payload efficient than smaller rockets, because adding more fuel also adds more fuel tanks, which are effectively just dead weight, so adding more fuel tanks has diminishing return. This can be seen in the fact that the price per kilogram of an Electron launch to a 550-kilometer low Earth orbit is $22,600 while the price per kilogram of a space shuttle launch to the same location was $54,500. And the Electron isn't even being reused yet. Imagine what would happen when they start catching Electron boosters with helicopters, which is actually something that they're going to be doing in the future. The current plan is not to use reuse as a means of decreasing price. It's more of a way to increase manufacturing, because they will no longer need to manufacture rockets as frequently once they have a reuse program set up. This will help them with their goal of launching every 3 days with a $5 million launch vehicle instead of a $6 million one. Of course, they're still a long way away from that. In terms of the actual layout of the Electron, at takeoff, it masses in at 12.55 metric tons. The first stage is 1.2 meters wide and 12.1 meters tall. It has 9 Rutherford engines and produces a total thrust of 162 kilonewtons at liftoff, and will eventually reach a peak thrust of 192 kilonewtons. Once the first stage burns out, it is jettisoned, and the second stage vacuum-optimized Rutherford engine begins to fire. It produces 22 kilonewtons of thrust in a vacuum, and has a specific impulse of 333 seconds. The second stage clocks in at 2.4 meters long and also 1.2 meters wide. Shortly after booster separation, the Electron's payload fairing is jettisoned. The payload fairing is designed to protect the payload from the atmosphere and to reduce drag. Once the Electron reaches space, it no longer needs the payload fairing because aerodynamic drag and heating are now negligible. During fairing jettison, the pneumatic latches on the outside of the fairing unclamp, which allows the internal springs to throw the sides apart. Once the second stage has burned out, if the Electron has to release payloads in more than one orbit, the previously mentioned Curie engine will fire. It will bring the payloads to their separate targeted orbit. The Curie engine is another thing that makes Electron unique. Most other companies, including SpaceX, are not capable of launching satellites to different target orbits. Have a nice day and don't die.